Assalamualaikum warahmatullahi wabarakatuh. Hello, I am Oke Putra. Today I want going to deliver our research on the high porosity and thermal stability polyvinylidene fluoride separator effect of solvent and copolymer colloidal SiO2 concentration. Separator is one component of battery. The separator doesn't carry out electrochemical reaction, but the separator play an essential role in main a battery safety by preventing physical contact between the electrode. The commercial separator use polyethylene or PE. Polypropylene or PP has a good mechanical property. However, it has poor resistance of high temperature and low porosity. In this research, the material with a higher melting point is used, namely polyvinylidene fluoride or PVDF, and will be produced to nanofiber membrane. The battery separator has a characteristic high ionic conductivity, good thickness and mechanical strength, good electrochemical and thermal stability. Nanofiber membrane are nanostructure has pore size 50 until 500 nanometer, high porosity, and high mechanical property. Nanofiber can be fabricated using several methods like a matte blow method, wet light, vacuum filtration, and electrospinning method. Electrospinning is simpler and has the potential to be mass-produced. Electrospinning is a method of manufacturing nanofibers membrane by applying a high voltage to the polymer. Research objective. First, to determine the effect of solvent and concentration of colloidal SiO2 on the result of the characterization of nanofiber membrane separator using the electrospinning method, and to determine the effect of using PVDF SiO2 nanofiber membrane separator on the performance of lithium-ion batteries. Method. The synthesis of PVDF polymer solution was dissolving 15% of PVDF mesh into the solvent PVDF acetone or PVDF ethanol with volume ratio of 7:3. The solution was stirred until homogeneous solution. Synthesis of colloidal SiO2 based on research conducted by Azlina et al. Was missing theos 18 ml, acetic acid 36 ml, and distilled water 6.4 ml. The solution was aging for 2 hours to obtain a colloid gel. The colloidal gel was then washed by ethanol and filtered to produce SiO2 residue. SiO2 was dissolved in varying concentration of 0 ppm, 1000, 3000, and 5000 ppm. Electrospinning process. The synthesis of nanofiber membrane with a double jet electrospinning method for 2 hours on rotating cylinder collector with electrospinning parameter, a high voltage of 15 kV, tip-to-tip collector distance of 17 cm, and a collector rotation speed of 150 rpm, then resulting PVDF SiO2 nanofiber membrane was dry at 80 degrees Celsius for 24 hours. In this research, 8 samples of PVDF membrane have been made. There are PVDF-A for DMF acetone solvent and PVDF-E for DMF ethanol solvent. Ppaer analysis. The results showed there are 3 strong peaks at indicating the functional group CF2, CH2, and CF as identified of PVDF. Several characterization peaks of the SiO2 overlap with the peak of PVDF. Membrane morphology. The formation of beaded membrane can reduce the uniformity of the nanofiber membrane. Beads are caused by interruption of the flow polymer jet due to the surface tension of the polymer solution. SiO2 concentration of 0 ppm are more uniform. This condition is due to higher net charge density or density compared to other concentration. Fiber size distribution. The difference of viscosity value causes the diameter of PVDF-E SiO2 is larger than that of PVDF-A SiO2. The higher of viscosity, the larger of diameter of resulting fiber. At 20 degrees Celsius, the viscosity value acetone is lower than ethanol. Porosity and electrolyte uptake. The addition of SiO2 concentration is increased the porosity and electrolyte uptake. Due to SiO2 is a material with porous structure to increase the space of the membrane as reservoir for lithium ion. PVDF-A SiO2 is higher than porosity PVDF-E SiO2 due to the smaller size PVDF-A SiO2 fiber. Shrinkage ratio of the membrane. Cutting the membrane in a circle and then heat it at 150 degrees Celsius for 30 minutes. Membrane shrinkage can be calculated using this equation. PP separator are damaged. The shrinkage of PP separator takes only 8 minutes because the melting point of PP is lower than melting point of PVDF material. The concentration of colloidal SiO2 can increase the membrane ability to maintaining its dimension because very high melting point of SiO2. The PVDF-E SiO2 membrane has the better capability. Acetone has a lower boiling point and a higher evaporation rate compared of ethanol. Mechanical property test. The higher of SiO2 concentration, the higher the tensile strength of the membrane because SiO2 enters the pore causes the pore size to get smaller and causes the membrane is become tighter. PVDF-A membrane has higher tensile strength value than PVDF-E membrane. The moisturize of PVDF-E membrane is higher than PVDF-A. Cylinder battery assembly. Using a cylinder cell with component nickel manganese cobalt or NMC for cathode, graphite for anode, and LiPF6 for an electrolyte. And separator using PVDF-A SiO2 and PVDF-E SiO2 5000 ppm and microporous cell guard or PP. Components are assembled on full cell lithium-ion cylindrical battery. Component size adjustment are 15 cm long and 7 cm wide. The battery charge-discharge test was carried out using a battery analyzer by placing a cylindrical battery on the battery analyzer probe. After connecting, it was set using the battery system test H or BSTH application. Charge-discharge test. Lithium-ion batteries using PVDF-E SiO2 membrane separator have smaller specific capacity. PVDF-A SiO2 membrane separator and PP separator have higher value. The lowest specific capacity of PVDF-E SiO2 is due to membrane damage during battery assembly. Specific capacity stability. The separator have retention ratio value respectively PVDF-A SiO2, PVDF-E SiO2, and PP are 88%, 59%, and 82%. PVDF-A SiO2 is higher than PVDF-E SiO2 and PP. This is proof that PVDF-A SiO2 has more stable specific capacity. Conclusion. The characteristic of membrane have porosity, electrolyte uptake, and tensile strength of the PVDF-A SiO2 nanofiber membrane were much higher than that of the PVDF-E SiO2 nanofiber membrane. This is because diameter PVDF-A SiO2 fiber is much smaller than PVDF-E SiO2. However, in the shrinkage ratio test at higher temperature, the PVDF-E is higher because it has a better thermal conductivity value. In testing the performance of the PVDF-A SiO2 nanofiber membrane battery is better than commercial PP separator and PVDF-E SiO2 nanofiber membrane. Acknowledgement. This research was funded by the Ministry of Education, Culture, Research and Technology Republic of Indonesia with this contract number